Hey, what's up guys? This is the second part of the video for section 10.2, which is simplifying radicals. And for today, for this video, we are going to talk about when you guys have a quotient inside of the radical or a fraction inside of the radical. So first, let's go ahead and look at the properties that you guys need to use when you guys simplify radicals. And there are two properties, so let's go ahead and look at those. So on the screen, you guys see the product property and the quotient property. Just a quick review on the product property when you want to simplify radicals. If you guys have numbers inside of the radical, you guys see right here, two numbers multiplying, you guys can separate the two radicals and simplify each one of them. So you take the first number, the radical with the radical, and the second number with the radical. Sometimes you guys are able to multiply a perfect square number with some other number inside of the radical. So that's going to help you guys simplify the radical. You guys can also go backwards. If you have two radicals, you're multiplying two square roots, you can make one square root, multiply the radicands, and then you simplify from there. Now today though, we are looking at the quotient property. So the quotient property says, you can separate the numerator and the denominator and make the radical for each one of them. So notice that here I have one radical and I have a fraction inside, a over b. So I can separate the top and the bottom, and I can use a radical for each side, the numerator and the denominator. Notice that we do have an n outside of the radical. That's because roots, we don't only have square roots, square means 2, but we also have cube roots, cube means 3, 4 roots, 5 roots, and so forth. My next video, you guys will learn about those different roots. But right now, we are just going to focus on square roots. So remember, quotient property, you can separate the top and the bottom, and you can simplify each one of the side of the fraction. Or you can go backwards. If you have two radicals in a fraction, you can make one big radical, and then you can simplify the radical, the square root. Just also a quick review. Perfect square numbers, you guys see those on the screen. I haven't talked about perfect cube numbers yet, because that's when you have the cube root. But right now we have a perfect squared numbers because we are going to have square roots. So all of these numbers here are perfect squares because they have a perfect square root. You guys can find a number squared that will give you each number on this list. For example, 9 squared is 81. 12 squared is 144. 5 squared is 25. 7 squared is 49. So every number has a perfect square root. Okay? So let's go ahead and look at some examples how to simplify when you have fractions in radicals. We have these examples here, and every example has a radical square root, and we have a fraction inside. Square root is when you find a perfect square number and you try to simplify it, or you can break down the number and then you guys simplify it. But I want you to understand what is the product, sorry, not the product, the quotient property with radicals. So let's look at the first one. And remember that we're not using a calculator. We don't want to approximate the answer. We're not using decimals for the answer, but we want to simplify all the way until we cannot do anything else with the fraction. So we have a square root of 49 over 4. Since the fraction is inside of the parentheses, I am going to make one fraction right here. And in the fraction, I'm going to separate the numerator and the denominator with its own radical. So the top, I'm going to have the square root of 49. In the bottom, I'm going to have the square root of 4. If you look at the numbers, 49 is a perfect square number because 7 squared is 49. So that means the square root of 49 is 7. Because if you square that number, it gives you back the radicand. And the 4 on the bottom, 2 squared is 4. So the square root of 4 is 2 because 2 squared equals 4. So I'm going to put the 7 on the top and the 2 on the bottom. So my answer is this fraction. I cannot simplify the fraction. You guys cannot reduce. We don't have radicals, so we have 7 over 2. Can you have a radical in your answer? Yes, you can. But I'm going to show you guys something that you cannot have in fractions when you have a radical for the next example. So let's go ahead and try the next one. Same idea. The quotient property says that you can separate the numerator and denominator. So I'm going to take the top, the square root of 25, and the bottom, the square root of 3. 25 is a perfect square number because 5 squared is 25. So that means the square root of 25 is 5. The bottom, you have the square root of 3. Now, 3 is not a perfect square number. 3 is a prime number. So what that means is you cannot break down the 3. You cannot find two numbers that multiply to 3 other than 1 and itself. So 1 times 3 is 3. But something else? No, you cannot. So that radical, that square roots, stays the same. Now, here's the thing with fractions. In a fraction, you cannot have a radical on the denominator. So notice that we have a square root on the bottom. That's a radical. We have the square root of 3 on the bottom. So we have to get rid of it. Every time you have fractions, you cannot have a square root on the bottom. So how do you get rid of it? You are going to multiply the numerator by itself. The number that has a radical, you multiply by itself. So square root of 3, I'm going to multiply by the square root of 3. And you guys will see right now that you get rid of the radical. But there's also another rule. In fractions, whatever you do to the bottom, you have to do it to the top. So you also have to multiply the top by the square root of 3. So let's look at the top. Here's my fraction line. On the top, you guys have a 5 times the square root of 3. 5 doesn't have a radical, so you cannot multiply the 5 and the 3 because this is not a radicand. It's not inside a radical. This number is a radicand. So all you do, guys, when you multiply 5 times the square root of 3, you put them together. You put 5 square root of 3. On the bottom, these two have a radical. They have a square root. So you can multiply the radicands, the numbers inside. 3 times 3. So that's going to be the square root of 9. 3 times 3 is 9. Now 9 is a perfect square number. 9, you can have 3 squared to equal 9. So the square root of 9 is 3 because 3 squared is 9. So I'm going to simplify. 5 squared root of 3 stays the same. But on the bottom, you guys have a 3 right here. So the square root of 9 is 3. Now I want you guys to notice something. Let's go back over here. Let's look at the answer, the denominator. Look back over here, denominator. The radicand is the one under the fraction. And that's what happens when you guys multiply a radical by itself. The square root cancels, and you guys keep the radicand. Okay? You can multiply the radicands. 3 times 3 is 9, but eventually you have to simplify it, and that's going to equal 3. Now, the next one, this is combining the two properties. You have the product property and the quotient property. Product property because you're multiplying, and we have two square roots, so that means that you multiply the radicands, and then inside of the radical, you guys have a fraction. So we are going to simplify the radical. So first, product property says you can make one big radical. I'm going to multiply the two fractions. So I'm going to have 6 over 7 times 1 over 3. When you focus on the fractions and you multiply fractions, remember that we can cross simplify. So the 6 and the 3 are cross from each other. You can simplify. 6 divided by 3 is 2, and 3 divided by 3 is 1. So you guys can simplify that. 7 and 1 cannot be simplified. So we have the square root on the top, 2 times 1, that's going to be 2. And on the bottom, 7 times 1, that's going to be 7. Now, remember, when you have the quotient property, you can separate the numerator and the denominator. So I am going to separate. I'm going to have my fraction line right there, the square root of 2 on the top, and the square root of 7 on the bottom. I separated numerator and denominator, and they both have a radical, square root. 2 is not a perfect square number. That's a prime number, so you guys cannot break down the 2. 7 is not a perfect square number. It's a prime number, so you guys cannot break down the 7. But we do have a radical on the bottom. So what we have to do is get rid of the radical. You multiply by itself, the square root of 7. and the top you multiply by the square root of 7. Whatever you do to the bottom of the fraction, you do it to the top. So now, guys, on the top, look, the 2 and the 7, they're radicands. They are inside of the radical, so you can multiply those two. 2 times 7. So I'm going to multiply 2 times 7, 14. On the bottom, well, you guys will have 7 times 7 is 49, but the square root of 49 is 7. So you guys put a 7 on the bottom. You can also look at it. When you multiply a radical by itself, the square roots cancels, and you keep the radicand. 7, 7, you keep the 7. Don't try to divide these two numbers because the 7 doesn't have a radical, so the quotient property doesn't apply. You cannot divide. The top number, numerator, has a radical. So my answer is this one. Square root of 7 is square root of 14 over 7. For the following radicals, you guys do have variables inside of the radical. So the idea is the same thing. You guys want to take the square root of the number inside, and then you guys will look at the variables, and I'll show you guys how to simplify those variables with exponents and a radical, the square root. So let's look at the first one here. You guys will start with the number, and you guys will break down the number, but I also want you guys to expand the variables that have exponents. So let me explain what that is. We do have a q as a variable, and this one has an exponent of 1, and we have a r with an exponent of 3. So when you guys look at the r exponent of 3, that means you're multiplying r by itself 3 times. Q to the exponent of 1, well, you just have 1q inside of the radical. So when I say expand the variables, is I want you guys to write down the actual variables multiplied by itself depending on the exponent that it has. So we do have the 75 here. There's the q, and I'm going to multiply by r times r times r. So those 3 r's came from the exponent of 3 for the r's. You are multiplying the 75 in the q, and the q times r times r times r. Now you guys will look at the number, and you're going to break down the numbers just like before. You guys will start finding two numbers that multiply to that. And I know that 25 times 3 is 75. And 25, you can break it down to 5 times 5. Once you guys have those numbers broke down, you guys use prime factorization, and you guys expand the variables. Look for pairs that will go outside of the radical. And remember that the square root is when you guys look for a number that you multiply by itself. That's why we're looking for those pairs, because when you multiply something by itself, that's going to give you guys the radicand inside the radical. So I know I have a pair of 5s right here. I'm looking at the q. That one doesn't have a pair, but I do have a pair of r's, meaning that I can make a group of 2 pair for the r's. This one cannot have a pair because there's no other r to make a pair. Now you guys will have your radical, and you put the pairs outside. So I have a pair of 5s, so I put the 5. I have a pair of r, I put the r, and then inside I have the 3. That one doesn't have a pair, so I put the 3 here. The q doesn't have a pair, and there's an r with no pair inside of the radical, so that one stays inside. That's the answer. The square root of 75 qrq is 5r times the square root of 3qr. Now, one thing that I want you guys to notice, this r has a pair, only one pair, and I put one r outside of the radical. If you guys have 2 pairs, you're going to have to put 2 r's. But what's r times r? It's r squared. So basically, you're going to put in a squared if you have 2 pairs inside of the parentheses. If you have 3 pairs, you use an exponent of 3, and so forth and so forth. So my answer, let me just put the box here, and we're going to go to the next one. The next one is you have more variables. So I'm going to expand the variables, and I'm going to break down the number. So for the 108, I'm going to leave the number for now. I'm going to multiply by x times x, and I'm going to do that 6 times because I have the x as an exponent of 6, x to the 6th power. So I'm going to have x times x, that's 3, 4, 5, 6, and the y is to the 4th. So I'm going to multiply y by itself 4 times, 1, 2, 3, 4. and the 6 has a fifth power. 1, 2, 3, 4, 5. Now I'm going to break down the number. So it's even, 108. So I know that 2 times some number equals 108, and that's going to be 54. 54 is also even. So I know that 2 times a number, which is 27. And I know 27, that's 9 times 3. And the 9, you guys can break it down. And that's going to be 3 times 3. Now that I expand the variables and I broke down the number, I'm going to start making pairs. So I do have a pair of 2's right here. I have a pair of 3's over here. This one you cannot make a pair. But now let's look at the x's. For the x's, I have 6 x's. So I'm going to start making pairs. I can make a pair of x right here. That's 1 pair. Another pair here. That's 2. And another one here. That's 3 pairs of the x's. So those are going to go outside. For the y's, I have a pair of y's right there. That's 1. Pair of y's right here. That's 2. So those are going to go outside of the radical. And for the z's, I have 1 pair, 2 pairs, and this one doesn't have a pair, so that's going to stay inside of the radical. Same thing with the 3 down here. This 3 is going to stay inside because it doesn't have a pair. So the answer, guys, you have your radical. So let's put the radical here. And the ones that have a pair are going to go outside of the radical. So I noticed that, remember, we have the 2 with the pair, and we have the 3 with a pair. So we're going to write down 2 times 3 outside of the radical. We also have 1, 2, 3 pairs of x's. So outside of the radical, you're going to put times x, and we're going to use an exponent of 3 representing the number of groups that we have. So we have 3 groups of x's, 1, 2, and 3. For the y's, we have 2 groups of y's. So that means I'm going to use times y squared. And the last one, you guys will have 2 pairs of z's. So we're going to have c squared. And I am running out of space here. So let me just do this here so I can have a little bit more space. I'm going to have times z with the squared. Now we are using the squared because we have a group of 2 z's. And we are using a square here because we have 2 pairs of y's. And we use the 3 because we have 3 pairs of the x's. Inside, you guys have the x, not the x, sorry, the 3 that doesn't have a pair, and the c up here. So these 2 are going to go inside of the parentheses. And you guys will multiply those. So we have 3 times z. Now let's make everything clean because I know the z, you can barely see it. But I am going to multiply 2 times 3. So that's going to be 6. We have the x cubed. We have the y squared and the c squared. And inside of the radical, 3 times z will be 3z. So the answer, when you guys simplify that radical, is right here. Now, just to make sure that you guys understand what the numbers come from, we do have an x cubed because we have 3 pairs of x's inside of the radical. We have the y squared because we have 2 pairs of the y's, and the c squared because we have 2 pairs of the z's. The 3 and the c, the one inside of the radical, they don't have a pair, so they stay inside. Now let's try another one where you guys have a fraction right here and here. I am going to change this fraction here. So you're going to see it differently. I'm just going to erase this one. And let me just write down the new one. This kind right here is one that we're not going to talk about yet. So let me write down the other fraction that I want you guys to simplify. So I'm just going to switch the numbers. And you see that the fraction's a little bit different. I added a k on the top. And I do have a k to the third on the bottom of the fraction. Now, every time you guys have fractions, I want you guys to look if you can simplify the fraction inside of the radical first. Meaning that if you can reduce the numbers, 8 over 3 you cannot reduce, but if you can, go ahead and do that. And also, reduce the variables that you guys have. Remember that the properties of exponents, they tell you that if you guys have the same base and you are dividing, you can subtract the exponents. So the k on the top, you guys do have an invisible 1 exponent. I can subtract the 2 exponents for the case, and since the biggest exponent's on the bottom of the fraction, that's where you keep the variable in the fraction. So let's go ahead and rewrite this. I have the square root here. I have my fraction, 8 on the top, 3 on the bottom, and I have a k squared because I do subtract 3 minus 1 is 2. And once again, it's on the bottom because the highest exponent is on the bottom. So now I'm going to separate the top and the bottom using the quotient property for radicals, for square roots. So what I mean is I'm going to have the square root of 8 on the top and the square root of 3k squared on the bottom. Now you guys have to simplify the top and the bottom. So let's go ahead and look at the top of the fraction. So I do have an 8, the square root of 8. So I'm going to start breaking down the 8 here on the side because I need space. So I know that's 4 times 2. And I know 4 is 2 times 2. Since I'm looking for the square root, I'm going to make pairs. So I have a pair of 2's. So that's going to go outside of the radical. And this one is going to stay inside because we cannot make a pair with that 2. So on the top, I'm going to have 2 square roots of 2. On the bottom, well, let's see. 3, it's a prime number. You guys cannot break down the 3. But the k, you have a squared. You guys can expand. So I have the square root of 3 times k times k. So the 3 is going to stay inside of the radical because that's prime. But the k, you guys have a pair. So that's going to go outside of the radical. So I'm going to have 2 square root of 2 on the top. And on the bottom, I take out the k because we have a pair. The square roots, square means 2, so you make pairs, group of 2's. And inside, I have a 3. Now we are almost done. One of the things that you guys have to be careful when you have fraction is the bottom, the denominator, you cannot have radicals. You cannot have square roots. So we're going to have to rationalize the denominator. Rationalizing denominator means you get rid of the radical, the square root on the bottom of the fraction. So how do we do that? All you have to do to get rid of this radical, notice the 3 has a square root, not the k, because you are multiplying these two, but the k doesn't have a radical, only the 3. To get rid of the radical, the square root, you are going to multiply the bottom, rationalizing the denominator, by the same radical. So we do have the square root of 3 on the bottom. So I'm going to multiply the top by the square root of 3. So now I'm going to have on the top the 2, the one outside, it stays the same because we are not going to multiply 2 times the one inside because you can't. The 2, this one doesn't have a radical. This one has a radical. So you can actually multiply those 2 radicands, the 2 and the 3, because they both have a radical. So I'm going to multiply 2 times 3, 6. On the bottom, I have the k. And I'm going to multiply the 2 radicals. 3 times 3 is 9. So I'm going to put the square root of 9. But hold on. What is the square root of 9? 3. So your answer is going to be 2 square root of 6 over k times 3, which equals 2 square root of 6 over 3k. Now, remember, this 3 here came from the square root of 9. Let me highlight that so you guys know where it comes from. So this square root of 9 is 3. And you just multiply the bottom. K times 3 is 3k. Now, if you notice, look at what happens here. There's a 3, but if you go up here, the radicand, when you guys multiply those 2 radicals, is 3. So that's going to happen every time you multiply a radicand by itself. You just keep the radicand. Okay? So when you guys multiply 3 times 3 is 9, but the square root of 9 is 3. So you go back to the number inside of the radical. So my answer is here. Do not try to simplify this 6 and the 3 because the 3 doesn't have a radical and the 6 has a radical. So you cannot simplify. They both have to have a radical in order to simplify. So let's try now another one with a fraction. So first, I'm looking at the fraction and I check if I can reduce the 68 and the 27. And nope, you can't. They don't have a common factor. but I can reduce the a's inside of the radical. These two here, they have the same base, so you guys can subtract the exponents. Remember, the top a has an invisible 1 exponent, so I'm going to subtract. The highest exponent for the a's is on the bottom, so I'm going to keep the a on the bottom of the fraction. The c, there's no c on the bottom, so you guys cannot simplify that. So let's just go ahead and simplify the inside of the radical. So I'm going to have 68 on the top, 27 on the bottom. A is on the bottom, and I subtract the exponents. 2 minus 1 is 1. Now, do we need that 1? Nope. So you can erase it if you want. I'm just going to erase it right now. And there it's gone. And the c is on the top of the fraction. So we have c cubed. Now you guys need to simplify the top and the bottom. But let's go ahead and separate using the quotient property. It tells you can separate the numerator and denominator with the square root. So I'm going to have the square root of 68, c cubed on the top, and then I'm going to have the square root of 27, a on the bottom. So let's go ahead and simplify the top first. I can break down the 68 and I can expand the variable. So let's look at the 68 first. I'm going to put 68 on the side. So let's see, two numbers that multiply to 68. Well, that's an even number. So 2 times 34 is 68. And I can break down the 34. 34 is also even. So you can multiply 2 times 17. 17 is a prime number. So you guys cannot break that number down, but we can make pairs. These two right here and these two right here make a pair. So that means that these will go outside of the radical and the 17 stays inside. And I'm also going to expand the variable because you guys will be able to simplify that. So I'm going to have 2 square root of 17, and let's expand the c cubed times c times c times c. So let's look for the pairs. For the c's, I can make a pair of c's. So I need to take that out of the radical because you guys have a pair. But let's put it at the bottom first. On the bottom, let's go ahead and simplify the 27. So the bottom 27, I'm going to put it right here. I know that's 9 times 3. The 9 is 3 times 3, and I can make pairs of 3's. So I'm going to put the 3 outside of the radical, and the a, well, before the a, let's not talk about the a right now. You have a 3 with no pair right here, so you're going to put that inside of the radical. So there's a 3 inside with an 8, and the a, since there's only one, you guys cannot expand. Now let's put everything together. Let's make everything clean. On the top, you guys have a 2c, and we have inside a 17 with a c, because this one doesn't have a pair. So there's your c. On the bottom, you guys have a 3 and the square root of 3a. Now, remember, on the bottom of the fraction, you guys cannot have radicals. So you have to rationalize the denominator. The only one that has a denominator on the bottom is this one here. So I'm going to have to multiply the bottom and the top by this one, because whatever you do to the bottom of the fraction, you also have to do it to the top of the fraction. So let's go ahead and multiply the bottom. I'm going to multiply by the square root of 3a. And now I multiply the top by the square root of 3a. So let's go ahead and see what happens. When you multiply the top, the 2c is not inside of the radical, so you guys keep that outside. 2c, you don't multiply. But now let's multiply the radicals. 17c times 3a, that's going to be 51. 17 times 3 is 51. And when you multiply c times a, that's just going to be ac. So that's on the top. On the bottom, you guys have the 3. So this 3, you keep it outside of the radical because you cannot multiply. But when you multiply these two right here, remember that you can multiply 3a times 3a. That's going to be 9a squared. But you guys don't have to do that, because when you take the square root of 9a squared, you guys will go back to this radicand. So you just put times 3a, which is the radicand inside of the radical. You simplify the bottom, so we have 2c square root of 51 ac on the top, and on the bottom, let me just put this up here, it's going to be 9a. So my answer is right here. So this is the last example I want to show you guys for this lesson, but I want to show you something else that you guys will probably encounter in the future, and you have to understand what happens when you have a negative radicand inside of the radical. So the next slide is going to be something extra, but it's going to help you guys a lot, especially when we start solving quadratic equations. But I want you guys to have an idea what you guys need to know. So you guys notice that all of these radicals have a negative number inside of the radical, okay? So that means the radicand is negative. When you guys have a negative radicand inside a square root, you guys cannot actually find the answer. But we use something that is called imaginary numbers in order to simplify. So let me explain what I mean right now. The square root of negative 4. We know that to find the square root of a number, you have to multiply a number by itself to get the radicand. So if you want to find a number that you multiply by itself and gives you negative 4, well, you guys are not going to find a number. Because if you multiply 2 times negative 2, you might be thinking that, hey, 2 times 2 is 4, so 2 times negative 2, that is going to be negative 4. Ah, you're right, but these two numbers are not the same. So you are not multiplying the same number by itself. So this doesn't work. Well, maybe you're thinking, well, what about negative 2 times negative 2? Well, yeah, those two numbers are the same. But when you multiply negative times a negative, it's a positive 4. So notice that this one doesn't work because they're not the same number. But this one doesn't work because we get a positive, not a negative 4. So what do we do in these cases? We use something that is called imaginary, just like I mentioned. And I'm just going to zoom out here so you guys can see. We use I for imaginary. When you guys see an answer with I, that means that we have an imaginary solution. It's not real. We just imagine what the answer is. And keep in mind that in a number system, we do have real numbers and imaginary numbers. But we haven't talked about imaginary numbers yet. That's going to be more for Algebra 2. But this is actually give you guys an idea of what it is. So how do we use imaginary? First of all, that negative inside of the radical, this one right here is going to turn into an I. So what I mean is, you put the square root of 4, just like the regular square root of 4 that you know, but you couldn't put an I at the end. And yes, I know this is a very funny I, but that's how I do my I's for imaginary. You guys have an I outside of the radical. This I means that this number came from a negative 4. Now you guys can actually find the square root of 4. Just the regular square root of 4 is 2. So the answer will be 2 with an I. And this is your imaginary number. So the square root of negative 4 is 2i. So let's try a few more examples. When you guys are looking for the square root of a negative number, well, first of all, you're going to change that negative into an I, and you have the square root of 64i, and the square root of 64 is 8, and you guys keep the I. So that is my answer, 8i. When you guys look at the square root of negative 25, well, the square root of 25 is 5, but since it's negative, you guys are going to have 5i, and that's my answer. And the last one, well, the square root of 121 is 11, but since you guys have a negative inside of the radical, you must have an I. So it's going to be 11i because it's a negative radicand. So all those imaginary numbers with an I means they came from a negative radicand. The number inside is negative. So like I said, guys, this is more for Algebra 2, but since we're doing radicals, square roots, you have to know what happens when the number inside of the radical is negative. Alright guys, so this concludes my video. Make sure that you guys watch my first part. This is the second part for radicals. And also make sure you guys practice, and I'll see you guys later.